Chapter 4 of our text contains a forensic analysis section on spectrophotometry. Spectrophotometry is a method of analysis where we look at what components of light a sample absorbs. We're going to take a source of white light and pass it through a prism or a diffraction grating, and then allow individual wavelengths of light to pass through our sample. And that sample will absorb light in either the visible or the ultraviolet region of the spectrum. This is a spectrophotometer from the late 20th century. You take a solution as your sample and you place it in a sample holder, and a beam of light runs through the sample, and then we analyze how much of that light is absorbed. An instrument like this can read light in the visible spectrum, but also in the invisible ultraviolet spectrum. This is what a 21st century spectrophotometer looks like. It's just a small USB device, still takes the same sample, but does not contain any of the complicated optics. It's all done by computer chip. So here's a forensic application of spectrophotometry. At a crime scene, I've discovered a small piece of colored paper. This could be from the wrapper of a piece of explosive. It could be ink from counterfeit banknotes. It could be from a threatening letter. It could be all sorts of different things. It could be the paint chip off a vehicle that's suspected to have been at a crash site. So what I'm going to do is I'm going to test that sample from the crime scene against something that I know the origins of, something that is my standard. This could be a paint sample from a manufacturer of a vehicle. It could be a true copy of the ink from the National Mint, or it could be, what the actual wrapper of a piece of explosive looks like. And I'm going to test to see if these two came from the same source. So I've dissolved the two colored samples in a solvent, and I have run that neat solvent through the spectrophotometer as a background. What I'm now going to do is collect the ultraviolet and visible spectrum of my unknown. And you can see that it has two major absorbances, one here in the purple part of the spectrum and one here in the red. Now, when material absorbs colored light, what happens is the light that is not absorbed, that light is transmitted. So our material looks green because it absorbs light in the purple and in the red. And I can look at this line and read that it is absorbing at right around 400, maybe 402 nanometers. That's a wavelength. And then in the red, it's absorbing at 669 nanometers. A nanometer is 1/billionth of a liter. Now what I'm going to do is switch out the sample for my known standard sample And what I see here is, yes, I still have a very strong absorbance right there, but it's about 670 nanometers now, so it's a slightly different absorbance. I've also got a shoulder here, and then the very intense blue that I saw in the first sample, well, that's gone. So these two samples, these two green dyes that could have come from, one came from a crime scene and one came from a standard, these are from different sources, which means I can rule out a suspect in my case.